Okay, so in this video we're going to start the second part of topic 4. Okay, and so topic 4 has 5 sections. 4.1, 4.2, and 4.3 obviously was part 1, and then part 2 is going to be over 4.4, which is called wave behavior, and then 4.5 is over what's called standing waves. Okay, and so our next test is going to be over those 2 sections, and then we'll be done with waves. Okay, so section 4.4, we'll probably spend the most time on 4.4. But part 2 of this unit is actually relatively short, and we're going to spend the most time on 4.4. And like I said, 4.4 focuses on what's called wave behavior. And so basically everything we're talking about in 4.4 applies to any type of wave, regardless of whether it's a mechanical wave or electromagnetic wave, transverse, longitudinal. Everything we're talking about in this unit applies to all waves. Okay, in 4.3, we talked a little bit about superposition, which is also something that applies to all waves. But then we talked about polarization, which only applies to transverse waves, and specifically we talked about polarization in the context of electromagnetic waves. But 4.4, everything in this section applies to any type of wave. And so we're going to start talking about reflection today just because it's the most basic type of wave behavior, and then we'll spend most of the rest of the unit talking about the other ones. Okay, so just a quick outline of what is in 4.4, the things you must be able to understand at the end of the section: reflection and refraction, Snell's law, critical angle, and total internal reflection. Those we'll talk about more in the next 2 videos, especially refraction, that's having to do with what's called Snell's law. And then the idea of critical angle and total internal reflection has some really interesting applications that we'll go through later on. Diffraction through a single slit and around objects. Interference patterns. We briefly mentioned the word interference before, but we'll go into more detail then later on. Double slit interference. And then the concept of path difference, which really mathematically speaking is going to be responsible for the types of interference that we see. Okay. As far as what you must be able to do at the end of this unit, you must be able to sketch and interpret incident, reflected, and transmitted waves at boundaries between media, solve problems involving reflection at a plane interface, solve problems involving Snell's law, critical angle, and total internal reflection, determine refractive index experimentally. We'll actually be doing a simulation lab where you do that. Qualitatively describing the diffraction pattern formed when plane waves are incident normally on a single slit. And then quantitatively, that means mathematically, describing single slit interference intensity patterns. And just some general guidance. It says quantitative descriptions of refractive index are limited to light rays passing between 2 or more transparent media. If more than 2 media, only parallel interfaces will be considered. Students will not be expected to derive the double slit equation that is given to you in the data booklet. Students should have the opportunity to observe diffraction and interference patterns arising from more than one type of wave. Now, as far as what's given to you in the data booklet for 4.4, you are given several equations, and we'll talk about all of these in due time. This first one is what's called Snell's law, and so that has to do with refraction. We'll talk about that in the next video. This equation right here is what's called the double slit equation. So later at the end of this unit, we'll talk more about the double slit experiment, which is also an interesting area of discussion, how this equation works. And then these last 2 are not equations per se, but they're basically mathematical conditions for constructive and destructive interference in terms of what's called path difference. So I will explain the concept of path difference later on, and I'll explain what these 2 conditions mean. Okay, so in this video, we're going to start off talking about reflection. Okay, so like I said, in this video, we're mainly going to focus on reflection, and we'll talk more about refraction in the next video. But reflection and refraction are both wave behaviors that occur when a wave is incident on a medium. Now, incident basically means that it hits a medium. And so I think we talked about media in the last video, or not in the last video, in the last unit. But a medium is basically the substance through which a wave travels. Okay, the plural of medium is media. Okay, and so here we have 2 media, air and glass. And so you can see this red arrow here represents light, in this case an electromagnetic wave traveling from one medium, which is air, into another medium, which is glass. Okay, and so you can get reflection and refraction when a wave is incident on a medium, trying to go from one medium to another, or just in general incident on a solid object. Okay, so reflection is a pretty straightforward wave behavior. And basically, you can see the definition of reflection here, but wave reflection occurs when a wave meets a boundary, such as a solid object, or it hits the interface between two media, and is at least partially diverted backwards. Okay, now, when we're talking about reflection and refraction, we always talk about with respect to the normal. So, what you can see here in this picture is these waves are drawn as rays, okay, as arrows, and you can see that the incident ray comes in, that's this purple line here, hits some type of reflective surface, could be like, a solid object, could be like, a mirror, could be the interface between two media, and then at least part of the wave is reflected back along the green arrow. Okay, now this dotted line that you see right here, this is what's called the normal. Now remember, the word normal is a mathematical term meaning perpendicular. So last year in IB Physics 1, when we talked about the normal force is always perpendicular to a surface. Okay, so here when we mean normal, we basically mean an imaginary line which is perpendicular to the surface that you're talking about. Okay, and so when you're talking about problems with reflection or problems with refraction, you always measure angles with respect to the normal. Now, as long as the wave is hitting a flat plane surface like this, then there's a very simple relationship between what's called the angle of incidence and the angle of reflection. The angle of incidence is basically just the incoming angle measured with respect to the normal, and the angle of reflection is the same angle measured with respect to the normal for the reflected ray. And for reflection, the angle of incidence is equal to the angle of reflection. And that's it. It's a very straightforward relationship. Now, keep in mind, by the way, that's only true if the surface that the ray is hitting is a flat plane surface. If it's curved, it becomes more complicated. But we're not going to talk about that in the IB physics curriculum. Okay, so theta incident equals theta reflect for reflection. Okay, that's also called the law of reflection. Now, in what situations do you see reflection? Well, reflection itself, like I said, is very straightforward wave behavior. Any type of wave can experience reflection. And just a few things about reflection. Again, that concept of the normal being the imaginary perpendicular line to a surface that's going to come up again. But as I was saying, some applications of reflection in real life include things like echoes. When you yell out into a canyon and you hear your voice come back, that's an echo. Okay, your sound wave is hitting some surface and it's being reflected back at you. Okay, sonar, radar, which is both used to detect things either in the air or underwater. Both of those use reflection. Okay, radar, you can think like radar guns that like the police use to see how fast you're using. They shoot like basically a microwave beam at a car, and it hits the car and reflects back, and that tells them how fast you're moving. Or if you imagine like air traffic controllers monitoring airplanes or helicopters in the sky, they use radar that where their radar dish sends out like an electromagnetic wave and it hits objects and it reflects back to the tower and tells them where the airplanes are. If you've ever seen a picture of a stealth plane, which looks something like this, notice that stealth aircraft are actually specifically designed to have very strange angles on their surface. And the reason for that is that when radar beams hit stealth aircraft, they're designed to reflect off of a weird angle so that they don't return back to the tower, and so that they're more difficult to detect. Okay, so that is another application of reflection. And also design of buildings and concert halls are also designed with reflection in mind, because when you're thinking of a concert hall with a bunch of musicians playing music, you have to consider that their sound will go off into the hall and reflect off of the different surfaces. And so you have to be aware of, what are the walls made of, what are the ceilings made of, are they angled correctly so that when sound waves reflect off of the walls and the ceilings, they reflect down to the people so they can hear them clearly, so it doesn't sound dissonant. And so there's lots of different applications of reflection in real life. Okay, so again, reflection is by far the easiest to understand wave behavior. We're not going to spend a lot of time talking about reflection, other than to just kind of show you basically the same type of situation we saw here, but maybe instead of drawing it with rays, showing you what it looks like in terms of wave fronts. Okay, so here the purple lines represent the wave fronts of a wave, and the green lines represent the wave fronts of a reflected wave. Okay, so here on the right side you can see basically what you see here in this picture is the wavefront picture of this situation right here, where you have an incident wave come in, hit a reflective surface, and get reflected back. Okay, so what you're seeing right here is the ray picture, and what you're seeing here is the exact same situation, just drawn with wavefronts. Okay, now one more key point before we end this video is keep in mind that during reflection, the frequency and the wavelength of the wave do not change. Okay, as we'll see in the next video when we talk about refraction, that's not the case with refraction. Okay, now how would you be able to tell if the wavelength changed based off of the wavefronts? Well, remember, the wavefronts of a wave represent where the crests or the compressions of the wave are. And so you can measure wavefront you can measure wavelength given a picture of wavefront just by taking a look at the distance between two wavefronts, and then that separation would be lambda, which is the wavelength. And so you can see here that the wavelength of the incident wave and the wavelength of the reflected wave, looks like a smiley face, kind of, is actually the same size. Okay, so there's no frequency change and there's no wavelength change of a wave during reflection off of the surface. In the next video, we'll see how that's different for refraction. Okay, so that is it for this video. Like I said, there's not a lot to reflection. Most problems you'll see in this unit have to do with other wave behaviors, but I at least wanted to get that out of the way. As always, please let me know if you have any questions, and I'll see you guys in the next video.